Hey there, Chem Squad. In today's class, we're going to look at kinetic energy curves or diagrams. Now, first of all, I want to talk to you about the difference between a spontaneous reaction and something called spontaneous combustion. The latter, spontaneous combustion, is actually a myth. Okay, this is where people have the notion that things can just combust without any extra energy being added to it. So it's like saying you have a set of paper that's sitting on your table, and then all of a sudden it just bursts into flames. So we know that that doesn't happen just because of activation energy. Now, the second thing is there has been a lot of talk in recent centuries about spontaneous combustions, that people somehow were bursting into flames. So even though this happened, a lot of the science behind it suggests that it is pretty much impossible because of activation energy. So I don't want you to confuse the term spontaneous combustion for something like spontaneous reaction. So spontaneous reaction is something that occurs. This is what happens when a chemical reaction can absorb enough energy, okay, so in our case activation energy, from the surrounding environment. So we've looked at this idea before. When this happens, we just call the reaction spontaneous. It's like mixing two chemical solutions together, and upon mixing, they simply react. Well, they don't react because they're spontaneously combusting or doing anything like that, but they are just gathering around energy from the environment. Now, the same idea doesn't apply to combustion reactions because the activation energy for combustion reactions are too high. Every combustion reaction that we know of, whether it's oil or alcohol, okay, in order for them to burst into flames, they need to actually have a spark or some heat source externally added to it. Those chemical reactants cannot absorb enough energy from the environment in order to combust spontaneously. So because of that, spontaneous combustions are basically a myth. There must be some kind of external source of energy that causes the reaction to happen. But since we're talking about spontaneous reactions, just drawing energy from the environment, that is something that's very plausible. And we're going to look at how we can figure out whether or not a reaction is a spontaneous reaction or not. So one of the things that we have to look at is called a KE diagram or a KE curve. Now, a KE curve is very different from a potential energy diagram. Here, we're actually measuring the amount of energy that molecules have to do work. So on the y-axis, we have the number of molecules present. When you're measuring a KE curve, it's always the number of reactant molecules, and we're always determining how much kinetic energy they have. So let's scroll down a little bit. Okay, so I'm going to draw out what we call a ideal curve, which is a bell curve. So it'll look something like this. Okay, so the plateaus on both ends are roughly about the same height, and the peak of the curve is actually in the middle of the diagram. Okay, so off to the left-hand side, we have the number of molecules. At the bottom, we have kinetic energy. I'm just going to label part of the graph. So at the top here, we have many molecules. At the bottom here, we have fewer molecules. And then in the middle, we have an intermediate amount of molecules, which I won't write in exactly right now. Okay. On the kinetic energy scale, at this end, we have low KE. In the middle, we have moderate KE. And over on the right-hand side, we have high KE. when we're looking at a Ke curve, it's different from a potential energy curve because we're always interested in the number of molecules that have a certain type of energy, okay, certain amount of kinetic energy. Now, usually, the whole mathematical physics side of this is that we look for the area underneath the curve, okay, but for chem, we'll kind of just point out which areas would have more molecules or less molecules, okay. So, for example, if we look at this bell curve, right in the middle, we have the peak, okay. So this region here, I'm just going to lightly shade it in as we go like this. This represents a large amount of molecules. So the majority of our molecules in this reaction actually have moderate kinetic energy. Okay, so a majority of molecules with moderate kinetic energy. If we look at the other end, the low Ke end, I'm just going to change the color here, we have few molecules with low Ke. With low kinetic energy. But if you look on the other side, the side that has high kinetic energy, we also find that very few of them have high kinetic energy as well. And this is normal. This is like saying if we were measuring the temperature of a room, that if the temperature of rooms is something like, let's say 20 degrees Celsius, okay, room temperature, I would say the majority of those molecules have an average Ke that gives you 20 degrees Celsius. But there are a few molecules elsewhere in the room that might have extremely low Ke compared to 20 degrees Celsius. It might have like 15 degrees Celsius. And on the other side, you have few molecules with high Ke that could put them into like 25 degrees Celsius. That's why temperature itself is just an average measurement of the amount of kinetic energy that's present. And that average is always underneath the peak of this Ke curve. So this is how we read a Ke curve. The information that we're given is the number of molecules with either high Ke, moderate Ke, or low Ke. Okay? So if we use this idea and we apply it to changes in temperature, for example, the graphs will shift and alter according to how much kinetic energy they have. So let's go down to the next diagram. So this diagram here, we have two kinetic energy curves. Notice that, again, we have number of molecules on the left and kinetic energy at the bottom. So first of all, I'm going to again write in low Ke, high Ke at this end, and moderate Ke in the middle. If you want to pause the video at this time to sketch out these two curves, okay, that's up to you. You can do so right now. Okay, so now that you have these two curves, let's look at what's going on between them. So the blue curve represents a Ke curve at lower temperatures. Okay, so let's say this is T1. Okay, so T1, let's say, is at 10 degrees Celsius. So you have a reaction that is happening at 10 degrees Celsius. And this one here is our T2. And let's say T2 is happening at 20 degrees Celsius. Okay, so almost double the temperature. Okay. So the one thing that we can say about T1 is that the majority of molecules have low kinetic energy, okay, compared to the T2. So this line here tells you that most molecules in the reaction have a lower amount of Ke. Okay, certainly lower than moderate. Okay. Over here, you have many, well, compared to the ones at high Ke, okay, there are some molecules with low Ke. Okay. Now, at this end, at the high Ke end, we can see that many molecules in the reaction or actually not many, but there are extremely few molecules there. So extremely few molecules with high Ke. Okay, and that's what you expect from a reaction that's at perhaps 10 degrees. Okay, if 10 degrees is a low amount of energy, kinetic energy, then you're going to see a majority of them that have lower Ke that amounts to 10 degrees Celsius. And at this end here on the left, where it has some molecules with low Ke, that could translate into something like you have some molecules that are at 5 degrees. You have very few molecules that would be above 20 degrees, right? Experiencing high Ke. So that's what the T1 curve tells us about the molecules in that reaction. If we moved on to T2, okay, we notice that there's a shift, okay, but there's other couple of things that we notice too. For one, the peak is lower than the first peak, okay. That's because most of the molecules that are at 10 degrees, okay, if you increase them to 20, most of them would actually have more Ke. So here's the thing. We don't expect it to keep its same shape. Okay, that usually never happens. Okay, because we're looking at number of molecules that have a certain amount of kinetic energy. So if I give more kinetic energy to the T1 curve, okay, raise the temperature enough to 20 degrees, well, it just means that overall there are more molecules with more kinetic energy compared to T1. So under this part here, we have, again, more molecules that have moderate Ke. Okay, so most molecules at moderate Ke. Okay, that might translate into 20 degrees Celsius because that seems to be the average. Okay, now because you've increased the heat, you've also increased the number of molecules that have high Ke compared to T1. Okay, so here you have some molecules. Okay, it's some because it's not most. So some molecules with high Ke. This should be higher than what you see for T1. Because T1 overall is at a lower temperature, there were fewer molecules of high Ke. But because you've increased the temperature, now more molecules on this end have high Ke for T2. Now, at the same time, we would expect even fewer molecules compared to T1 to have low kinetic energy. So here we have very few with low Ke. Okay? So whenever you're changing temperature, you need to have two graphs in order to make the comparisons. Okay? They're relative to each other. So we can see the temperature effects, what temperature effects have on the number of molecules, okay, compared to their kinetic energies when we increase temperature. But this isn't the only thing that we can do with Ke curves. Okay? There's something called activation energy threshold. Activation energy threshold is pretty similar to activation energy on a PE curve, okay? But it's seen in a different way. So I'm going to scroll down again, and here you see again two different graphs, but there's a dotted line that's roughly in the middle. Okay? This dotted line is what we call activation energy. Okay? On a Ke curve, it's sometimes called threshold energy. But activation energy works just fine. So if you want to pause the video here, you can take your time and sketch out the two curves. Okay, make them similar to what I have shown here. So what we see now with the presence of activation energy. Now let's look at this darker curve first. Okay, the majority of molecules have less energy than the activation threshold. Okay, so most molecules do not have enough activation energy. Okay, so if they don't have enough activation energy, they're not going to react. But if you look at this side here, okay, you have few molecules with enough activation energy. So a few of these molecules might actually be going through a chemical reaction just because they have enough activation energy, but the majority doesn't. So overall, this reaction is non-spontaneous. It cannot absorb enough energy from the environment to react on its own. So it needs additional energy in order to react. So it needs additional energy to react. Okay, so you just have to give it enough energy to get over that threshold energy. So that's where we are with the second curve. So the second curve here, you'll notice that most of the reactant molecules actually have more than activation energy. Okay, so everything that we actually see here on the right side of that threshold, that means most molecules have enough activation energy. Okay, so here the overall reaction means that this reaction will be spontaneous. So it's a spontaneous reaction. We don't need to add more add more energy to it. Okay, it does not need any more external energy. It can gather enough energy from the environment in order to react on its own. So that's why it's called spontaneous. So it always depends on where the activation energy is. So that means, if we were to summarize things a bit, okay, let's see if I can lower this down a bit. Okay. So summary-wise, if the peak of that curve, of your KE curve, is to the left of the energy threshold, or activation energy, then the reaction is non-spontaneous. Okay. If the peak is on the right of that energy threshold, or Eact, then the reaction is spontaneous. Okay, so that seems pretty simple enough. So always look at your KE curve. If the peak appears on the left, you have a non-spontaneous reaction because most of those molecules do not have enough activation energy. But if the peak is over to the right of the activation energy threshold, then most of those molecules do have enough activation energy to react on its own. Now, I'm going to leave you with one final thing. We're going to go back to the last diagram here, so I'm just going to scroll up just a little bit. Let's say we add in a catalyst. Okay, so if you add a catalyst to a reaction, it typically lowers the activation energy. So what do you think would happen if I added a catalyst here? How is this graph going to change? Well, the graph itself, the curves itself, do not change. But when you add a catalyst, it's the activation energy or the threshold energy that will move positions on this curve, on this graph. So in red, I'm going to say this is add catalyst. Okay. The effect of adding a catalyst is to push or move the activation energy threshold over to the left. So this is the activation energy with a catalyst. So by pushing the activation energy to the left, we can see that this slow reaction, the one that was non-spontaneous before, might become a little bit more spontaneous, or at least it would react quicker. It actually has very little effect on the orangey-yellow curve because, again, it just means that more molecules have enough activation energy, so it still remains spontaneous. So the effect of adding a catalyst means that we're going to shift the threshold energy over to the left, therefore speeding up the rate of reaction. Alright, that's all the time I have for you guys today. I hope all this makes a little bit more sense. I will see you guys soon. Thank you.